Well, I'm delighted to see so many people. I think it's great.
Yeah, is there anything you would like to say first, Todd? Like more broadly related to COFFIES? My introductory remarks are really about the near surface shear layer.
Well, I didn't prepare anything, but I can always talk about COFFIES. So most of you know that we're a Drive Science Center, that we're just getting started. So we had a 2-year process of writing a proposal, and it finally was accepted, and now it's actually funded for most of us who are part of the team. And we're delighted over the next 5 years to bring together not just the people who are, part of COFFIES in the inner circle, but also broaden the circle and have people from all over who are interested in the same topics work together. And so we're trying to be as open as we can, and we encourage people to participate and to collaborate. And this is really sort of our first kickoff of what are our 3 themes. So we have 3 themes in COFFIES. All of us are trying to figure out, why is there a solar cycle, and what's the next one going to be like, and how predictive can we be? But that really breaks itself down into a number of different science questions. And what we've done in the course of the 2 years is identify 3 places where we think there can be real progress in the next few years. So one is the tachocline, that's the bottom of the convection zone, where many of us think that the dynamo is acting, but not exclusively there. The second is flux transport and emergence. That's really why active regions form where they do, what triggers the release of flux from the inside, does flux make its way to the surface, and what's imprinted on that in that process of going from the bottom of the convection zone or wherever it comes from to the surface. And then the near surface shear layer is what we're going to talk about today, and we're going to get into a lot more detail, but that's the region near the surface of the sun where conditions change a little bit. And we can't quite see it, but we can almost see it. And there's some real hope, I think, with the helioseismology and the brains of all the people on this call, and a few others probably, to really understand more over the next few years about what we're doing, what the sun is doing, and how it works. So I don't have anything else specific in mind, but I'm really delighted to introduce Rudi and Nick, who are leading this group. So carry on.
Great. Okay. Well, we're at 10 after, so I'll just get started. I'm here just to provide a few slides to kind of get everybody's mind into the topic of the near surface shear layer, but I'm not actually presenting any scientific results or anything like that. So let me share my screen. Okay. Do you see my slide?
Yep.
Okay, great. Yeah, so I'll just get started. So just briefly, all I'm going to touch on is, why we might be interested in the near surface shear layer. What did we propose to do at a very high level as the COFFIES, as part of the COFFIES Drive Center project. And then just a bit about kind of today's meeting and how we sort of hope the discussions will go. So, the near surface shear layer is this region, and kind of the outer 30-ish megameters of the solar convection zone, where the strength of the differential rotation diminishes pretty substantially. And so this raises a couple of questions sort of right off the bat, and these questions will kind of weave their way through really any of the discussions today. And those really are, how does this even happen in the first place? Why is there a near surface shear layer? What processes maintain it? And then also, what is its relation to solar magnetism and to the dynamo? Is this region of the sun sustained somehow through Lorentz forces? Do those form an important part of the angular momentum transport in this layer? But then also we have this region of shear. It's not as substantial as that in the tachocline, but is it possible that this has some bearing on the dynamo? And then of course all of the flux that we see emerge at the surface of the sun has presumably transited through at least some portion of the near surface shear layer. So those are kind of the big questions. Why is it there? What's its relation to solar magnetism? But it's also interesting to me as a kind of a convection focused person, and that this region of the sun really is also our window into the deeper convection zone. Through global helioseismology, of course, we can measure the differential rotation throughout the convection zone and down into the radiative zone. But when we're asking questions about the convection itself, we can only measure that with local helioseismic techniques. And it turns out that our ability to probe in depth with local helioseismology, or the depths to which we can probe, actually more or less coincides with this region of near surface shear in the sun. And of course, when we have looked at convective flows in this region, we've seen some surprising results. We've seen some disagreement between time distance and ring diagram analysis techniques. We see that, you know, the surface of the sun is covered with you know, photospheric granulation, but then also that seems to organize into the larger scales, supergranulation, kind of 30 megameters, which is roughly commensurate with the depth of the near surface shear layer. And we don't see any flows on larger scales. And for various reasons related to theory and related to results from numerical simulations, this is puzzling. We would kind of expect to see convection on scales maybe commensurate with the depth of the convection zone, or somewhere between supergranulation and the depth of the convection zone. And we don't seem to see flows on those scales, at least with the sort of power we would expect if they were part of a larger convective spectrum that extended past supergranulation. Of course, what we do see in this region, it's a very dynamically active region of the sun. And in recent years, we've started to realize that there are probably some additional clues to what's going on deeper in the convection zone in this region. Here I'm just showing some results from tracking kind of supergranular sized structures with Dopplergrams from David Hathaway and Lisa Upton from a few years ago. And you see these large scale flows, but they're much weaker than we would have expected. And it turns out that at the equator, these are Rossby waves. And then in the polar regions, and here on the right, they've got kind of this nice projection they did where they used data from a long time series and sort of wrapped it around the poles. There's this spiraling structure that you can sort of see with your eyes. And, you know, there's some question, you know, what is this? Is this convective? Is this some kind of vortex? And, you know, this recent work by the Max Planck group, led by Laurent Guizon, there's a very nice paper from last year, which very convincingly identified these structures as inertial modes. So these are wave modes whose restoring force is the Coriolis force. And they've done some nice work with this. Several of you attended a talk by Yuto Becky last week, kind of looking at these sorts of features and how they pop out of numerical simulations. And so, you know, it's not just the region that we can probe helioseismically, but we're actually finding that there are different wave modes that we can sample in this region. And I think there's going to be some interesting results coming down the line in the next few years where different research groups start to learn what we can actually do with these observations and what additionally we can learn about the interior, the deeper convection zone. It's also interesting from the standpoint that it is presumably a region where the dynamics transition from a state where the flows really are not influenced by the Coriolis force. So if you think about the lifetime of a typical supergranule and its speed, it's really just too fast and too short-lived to be significantly influenced by the Coriolis force. Deeper down, though, just by virtue of the fact that the sun has a prograde equator of differential rotation, we think that the flows deeper down must be significantly influenced by the Coriolis force, and it impacts their structure of those flows and the way in which they transport angular momentum. And if this were not the case, we would expect instead to see that the sun had fast poles and a slow equator. That is what tends to arise when you have convection that is kind of essentially isotropic. And it's sort of mixing angular momentum all over the place, as opposed to having some anisotropic, strongly anisotropic component to its angular momentum transport. And so when we're looking through the near surface shear layer, in principle, we're looking at a transition between rotationally dominated and non-rotationally dominated dynamics. And so that's interesting as well. And it turns out it's very challenging to simulate. Later today, Hideyuki Hotta, who I am kind of hoping is still sleeping at the moment, will be presenting to us at 6 a.m. his time from Japan. And he's going to talk to us about some recent simulation work he's done that seems to really do a good job at reproducing the near surface shear layer in a self-consistent fashion. But until we see that, I would say kind of the state of things is that it's very tough to get one of these to set itself up in a model that is, fully nonlinear and includes what we think are the salient physical effects in the convection zone. And it tends to be that when we try to model this region, you only get kind of a shear-like layer in the equatorial regions of your models, and not in the mid to high latitudes. Okay, so that's sort of just a brief overview of maybe why this is somewhat interesting to talk about. And I hope with all of the different attendees on here, you have completely different ideas about why it's interesting to look at this region of the sun. And I hope you share them today. As far as the COFFIES Drive Center goes, we kind of have these sort of three overarching scientific goals related to the near surface shear layer that we hope to pursue over the next few years. And the first is, we really just want to characterize the dynamics of this region and understand the processes that give rise to the near surface shear layer. We'd also like to understand what its implications are for the deep convection zone dynamics. And so as we get a handle on point one, we'll probably implicitly get a handle on point two. Why is it there in the first place? Why doesn't the solar differential rotation that we see in the bulk extend to closer to the photosphere? Or conversely, why doesn't the near surface shear layer extend deeper into the sun than it does? And then we would really like to understand how this is related to the broader dynamo process in the sun. Okay, so last slide. So today, what we are really trying to do is spur discussion. So we have just a handful of talks where we asked a few different people to come and present on some recent results of theirs related to the near surface shear layer. So we've got Rudi Komm, Irina Kitiashvili, Kyle Augustin, and Hideyuki Hotta, who will be speaking to us throughout the day. But in between these talks, what we want to have is some open discussion. And so we encouraged people to submit some ideas for discussion. We got a handful of ideas, and so those are in the agenda. What's on the agenda is not exclusive. If you have thoughts that come up as someone is presenting, pull together a slide or pull a plot up from a paper and feel free to share it. Because what we would really like to get out of this is some ideas from the community of what should we be focusing on together as a community. How can we collaborate? What are the problems we should really be thinking about related to this region? And how do we pursue solutions to those problems or better understanding? And so, again, please, if you have thoughts, in the discussion sessions, feel free to share them, share slides. Don't worry if you haven't told us yet. This is meant to be free form. And we've just asked the folks that submitted some ideas to provide a couple of slides to kind of kick things off in these different discussion sessions. And with that, I will stop. I don't have any more to say. Thank you all, and I look forward to chatting with you today. And so maybe to kick things off, we'll just move right on to Rudi.
Yep. Okay, then I will see if I can share my screen. The usual, where is my button? Okay. And I hope you see something here that looks like.
You got it.
Yep, looks good.
Do you see something? Okay.
Yep.
Okay, good. So yeah, I will talk about the radial gradient of the rotation rate as Nick has already pointed out. The question is what happens to the rotation rate and goes on. Oh, most of what I talk about, or a large fraction of it, will be about recent results by Antia and Basu in 2022. That's a very nice paper about that. And Sabani is traveling, so that's why I talk about this and include some of the ring diagram results, stuff that I've worked on. So that's what the reason is why I'm giving a talk, even though I'm one of the organizers. So yeah, this is just first a few introductory things, just so as a reminder that the near surface, that there is such a thing of a near surface shear layer, sort of started to come out in the early 90s from some of the helioseismic observations. And so I just sort of showed you that by now it's actually what, 30 years that one knows that there is a near surface shear layer. And so that is one of the first papers that I could find, Ed and company. And so then there was the question, okay, if we have this kind of near surface shear layer, then obviously the radial gradient has to be negative, because if at the surface, if there's a local maximum at the depth of 0.95 roughly, then obviously the rotation rate decreases towards the surface, and that means the radial gradient is negative. But what value would you think it should be? And so there was, if one makes an angular momentum conservation argument and sort of thinks of them, maybe it's the supergranules, the convective motions, etc., then you would think that if you take the log, the d log omega, d log r, then it should be something like -2, right? But what the observations show, it's -1. And that was sort of from early on, sort of Kobar and Thompson in 2002, they used some MDI F modes, and they could quite nicely see, I don't know, can you see my cursor? Or is it? It's okay. So it's quite nicely to see that this is the gradient is roughly -1 as a function of latitude. And so that is then also kicked off, as Nick already said, the different question, why is it there? Why is it the thickness? Why does it have the extent it has? And what kind of influence does it have? What does it mean for convection, for the magnetic flux, etc.? And so the results that I'm going to show is from this paper, and I asked Sabani, what are the points that I should emphasize here? And the answer was they used they used MDI data, GONG data, HMI data, okay? And yes, there is always some difference between the different instruments. That's as you might expect it, but nevertheless, you can clearly see there's a temporal variation, and you can also see that the extent of the near surface shear layer also varies with time and varies a little bit with latitude. So these are the points that are going to show you in the pictures. So this is the one where you see the d log omega d log r, the non-dimensional radial gradient. This is what I'm talking about, because then it's -1 at 0.99. This is where the arrow points at. The different colors are the different depths. The x-axis is latitude, and the y-axis is the value. And so you see at the close to the surface, as you can go with global, that's just usually 1% down from the surface at radius 0.99. There you get the -1. That pretty much there's been lots of observations between Kobar and Thompson and Antia and Basu, and they all come down to it's roughly -1. And then as you go deeper, red is at 0.97 and blue is 0.95. Then obviously the gradient gets smaller because you get closer to the local maximum. So yeah, it will go to 0. And the difference, what the different lines, like the solid line is MDI, dashed is HMI, and long dashed is GONG. And so you can see they all show the same behavior, but it's always a little bit different, right? And what they pointed out is that this sort of wavy undulative behavior in the GONG data is most likely due to that they use, they don't go to quite as high degree modes as the HMI MDI go, and also they use 8 splitting coefficients to for the function of latitude, and so you end up with that. And to see whether that hunch is correct, what they did, they limited the HMI data to 8 coefficients, and then you get the dotted line, and so yes, you get this kind of behavior. So this is just a function of that. So one can understand where this comes from. And the other thing, what they did in this one, I should point out, because you have noisy data and you have to take the derivative of them. So what they did instead in this one, they used splines. They fitted the rotation rate with splines, so they didn't have to take a numerical derivative. And I think that's, and the other thing, what I should point out, again, what others have also seen before is that as a function of latitude, it's relatively constant, right? I mean, there's a little bit of an increase, but it's only when you go to high latitudes, like 60 degrees, then things sort of fall apart. And that might simply be foreshortening. That might be geometry, okay? So that your resolution goes down as you go closer to the limb, or go, yeah, in latitude or in the other direction. And then we're always interested in solar cycle variation, right? I mean, pretty much all the things that we can measure on the sun, the question will be, is there a solar cycle variation in it? And so this is different examples. The top one is at the close to the surface, 0.99. X-axis is now in years. The y-axis is in latitude. And what you see is then take the residual. So what you do in order to show a temporal variation over the solar cycle, what you do is you remove the temporal average at each latitude, because otherwise you just, especially if you do, for example, just with the rotation rate, it's just dominated by the differential rotation, you see nothing. And so that's why in all these kind of plots, when you see solar cycle variation, there's always most of the times the temporal variation has been subtracted for each latitude. And so what you see is quite nicely, the behavior is sort of at the top. My internet connection is unstable, it claims. Okay, so quite nicely, you see that on top, close to the surface, where the activity is, it's blue, which means it's more negative. So that means it's anti-correlated with the activity, and the bottom 2 panels that it's at 0.95, there you see where the activity is these sunspots, things are these little black dots in there. And so with the red colors, you can see that, yeah, they line up nicely where the radial gradient is more positive, which means it's flatter, right? I mean, since the radial gradient is negative, so if it goes a little bit in nudges, then it nudges towards 0, is what that means. And so deeper down, it's correlated, and closer to the surface, it's anti-correlated. And so you have this kind of radial dependent. At the bottom, there's also the 2 different, one is MDI HMI, that's the middle panel, and the bottom panel is the GONG data, and they all look reasonably similar. You have this kind of variation with time. So there's clearly a solar cycle variation in it. And if you grab then, let's say, this is at 20-degree latitudes, if you take that and then do a slice as time and depth, then you see in the top one, this is the MDI HMI, then you see this transition between anti-correlation and correlation. So the colors change, the depth of 0.96-ish, closer to the surface, it's anti, and deeper, it's correlated. And in the Gong data, you don't see that. You see the correlation deeper down, but near surface, they say, well, again, due to the lack of the modes and the fitting as it's done, there, that most likely explains that there you don't see it simply because you don't have the information there at that depth. So for the closer to the surface, they would trust the MDI HMI data set. Okay, so there's clearly this. It varies with the depth and radial extent. What they've done is they say, hey, since the near surface shear layer is defined as the region from the surface to where the local maximum is, how about we say the strongest gradient will be close to the surface, so we take the maximum value and then say anything that is above 20% of this maximum value is the range of the near surface shear layer. And so that's what they've done. And again, as a function of latitude, what you see then is that, again, depend on what you do, you get something that's a little bit different. The red ones is HMI MDI, and so you see it's basically 0.95-ish. And the blue and black ones is Gong, and you see again this kind of undulation with latitude. And again, this is due to the limits in the splitting coefficients used. If they limit the HMI data, then you get the dashed sort of, I'm not sure, cranberry. I'm not sure what kind, what kind of color that is, and then you get something that is even lower. So yeah, that explains that. So roughly it's the 0.95, as we all know. And there is the one curiosity is that maybe it increases a little bit with latitude, which means the near surface shear layer gets shallower as you go away from the equator. And you see that at the equator, it's sort of a little dip. It's almost like it's a little bit deeper at the equator than at, let's say, mid-latitudes. Mid-latitude is for me like 30 degree-ish, okay? And at high latitudes, which means 60-ish, then again, the different measurements show different things. That's where things are not as reliable as one might like. But as you heard from Nick, the models find it easier to create a near surface shear layer at the equator. So maybe this means something here, that the extent of the near surface shear layer, even the sun seems to have it easier to create a near surface shear layer at the equator than at mid latitude, even though it's just a smidgen. I mean, it's a teeny tiny difference, but just as a provocation here. And again, solar cycle variation, is there one? The answer is yes. And so what this shows is this top MDI HMI and bottom is Gong. They both show the same thing, and it looks like where the activity is, where the swarm of black dots are, that there it is a little bit more on the yellow side, right? I mean, it's greenish, but it's a bit more on that side, which means where the activity is, the near surface shear layer is shallower, right? I mean, you could sort of conclude that from the solar cycle variation of the gradient, right? Because it goes a little bit more positive. It's correlated. So it goes a little bit more positive, which means it's smaller in magnitude, which means if you take 20% of the maximum as your measure, then of course the extent of the near surface shear layer will move closer to the surface. So that is what this shows. If you have magnetic activity, excuse me, then you end up with a shallow near surface shear layer. And that is sort of what the three bullets that I showed early on, the instruments show the same, but slightly different. And there's clear solar cycle variations. And if you get closer to the surface, then it's anti-correlated, which means, excuse me, the gradients go steeper, while in deeper down, the gradients go flatter. And so the extent of the near surface shear layer also varies with time, and it's shallower at location of high magnetic activity. So then, this is all global results. And early on, Zatri and Kobar, I think, were the first ones to try to use local, excuse me, use a ring diagram technique. And they found something that, yes, it's sort of, they didn't do the non-dimensional, the log gradient. They did have, it's the rotation rate is in nanohertz and then just that. But still, you see something that it's with latitude, sorry, with latitude, it's pretty constant. And what you see there difference, because with local stuff, you can't go as deep, but you can get closer to the surface compared to global. And there seems to be, it gets a little bit steeper as you go closer to the surface. So now that brings me to my results. And I've been looking at the zonal flow for quite a while. And this is a plot where I overplotted the typical size is 15-degree ring diagrams. That's usually what you see in papers. The Gong and the HMI pipeline produce that. The JSOC, the HMI pipeline uses also 30-degree tiles, which can go a little bit deeper, which is the red dots in these plots. And you can go cover pretty much the near surface shear layer with that. And so what this is a comparison of the average as a function of depth in megameters. This is, I usually think in megameters, not in radius. And the flows are given in meters per second. Again, I don't think in these other quantities. And so what you see is that the rotation rate, as you should, as you expect, it increases with increasing depth, and then it sort of flattens out at around the 35-ish megameters, because that's the 0.95 in radius. And so what you also see is that close to the surface, the increase of the zonal flow is a little bit steeper, and then at about 8 megameter-ish, then it's a little bit flatter, but still increasing. And so the arrow points to the 30-degree at that thing. In the HMI data, this variation is so pronounced that it almost looks like a little local maximum. The Gong data show it too, but it's much subtler. It still is steeper, close to the surface, and then goes a little bit flatter. And the reason why I'm going on about this is because if I show you the radial gradient, the derivative out of this is strictly numerical derivative, then you should not be too surprised that 30 degrees now at the bottom, that out of HMI data, you get something that is at that depth much closer to zero, simply because it's a local maximum in the zonal flow or the rotation rate. And so, but overall, and the Gong is again not as pronounced. Still, it looks reasonably what you might expect, that roughly at 0.99 you get sort of the -1, and as you go deeper, follow the red circles towards 0.95 on the left, you end up with something like -0.1, -0.2 in that kind of range. And that is what the global results also show. So I mean, you expect differences, you use different techniques, but they're sort of similar in the qualitative behavior. And again, as you already saw in Ames and Thierry's plot, when you get close to the surface, when you go from 0.99 to the right, closer to the surface, it goes steeper. And then what you also see here is when you go very close to the surface, then the error bars just go large, and you might not want to believe it. Okay, so this is then just where, things are simply, you run out of modes and it gets trickier. And so it's understood that their things are not as reliable, but it shows you that to, let's say, 0.997, 2 megameters is roughly right. And so the thing is then it looks on with the different in the zonal flow and here in the radial gradient, it almost might imply that are there two different regions of the near surface shear layer? And I think Irina will tell us more about that. And so this is just a few things to sort of show go along the lines with the global results. This is now radial gradient with latitude as at 4 different depths. And just like at the top left one, this is the one close to the surface where I still sort of trusted. What you see is error bars are large, but still, even with all the wiggles about, one could easily put a horizontal line through that would go through pretty much everything, and you would say, it's at -1 point and a bit. So I think it's still pretty good what you see here, and you see that it is relatively flat with latitude, which is nice, because that's what the reason why it's nice is with the local results, because you can measure the 2 hemispheres independently and the different points. So you would be able to discover if there's like a gradient between the hemispheres or some variation between it, because the global, by their nature, it's an average over both hemispheres. So you could have some elaborate wiggles with latitude and you would not see it because it would just average out, right? So in that sense, this is nice that yes, it confirms that, and yes, if as you go to higher latitudes, eventually foreshortening will catch up with you and your information will go down. So you see some other variation. Now, for the amusement, I combine them into functions of latitude and radius. The left one is a 30-degree HMI, the others are the HMI and the gong. And what you see there is, and the color is chosen so that -1 is the dividing line between the blue and the red ones. And so basically it's just a visual to see that all of a sudden I seem to have an echo in my voice. So if I'm speak a little bit different, that is for that reason. So at 0.99, as in the global, it's pretty much flat and it's -1, and pretty much in all 3. And in the gong data, you see these funny things, but if I go back at the top left ones, there you can see the black diamonds, they sort of wiggle a little bit. They have sort of almost, I had not thought of it before, but it's almost like the global results, they also show some, I do not know why that should be rings, because they treat each patch individually, so it should not matter. But there seems to be some kind of undulate. But still, if you squint and sort of in your mind average over that part, in the gong data, even though there's some wiggles in it, but still from 0.99 closer to the surface, it's blue on average, which means it's steeper. And if you go deeper, then things go flat as one expected. And at the high latitude, you see then, especially in the left one, sort of these kind of variations with depth. Most likely it is like the ones from the global results saying, it's probably foreshortening. But there could be also, what if the radial gradient would not be monotonic, then these different things would just, the different results that you see in global might just mean that the different measurements have a subtly different average in depth. And so they might just reflect that. So I think that is something that one could follow up with, let's say, 30-degree tile rings from gong, for example, because gong and HMI have different systematics. So you see that in the Murnau flow, where do counter cells appear? I mean, that counter cells as equatorward Murnau flow at high latitudes that appear if the B angle is against you. And so they're clearly, they have annual variations, they go by the B angle. And so they are different between HMI and gong. And so that would be one way to check, is it all just foreshortening or is there more to it? At this point, most likely foreshortening. But anyway, solar cycle variation. And that is, now I use strictly the gong data simply because I have 2 solar cycles worth of data. And so the top one is the one at 2 megameters, the 0.997, where things begin to break down, and the others are 0.99 and 983. in depth. And so you see that kind of in the middle and bottom panel, you see the kind of anti-correlation that you also saw in the Antia Basu in the global results. So that all goes together. And so the top one shows a correlation, and sort of that is in that sense sort of reminiscent to what they see deep down. So if this can be verified if we have more HMI data as time progresses, and one can do a nicer comparison that way, one should be able to see, because it could be, at this point, it could be noise, okay? But, it's just harder to say. But it could be that in the bulk of the near surface shear layer, the radial gradient is anti-correlated with activity, while at the top and at the bottom, it's correlated. And I should also say, this, of course, this picture is not what the raw data show you. As you could see from the Gong data, you have this kind of variation with latitude. So I took that out. Removed the temporal mean. And at the one close to the surface, there is also seems to be like there's a difference, an offset between before and after 2015, and I have no idea why that is, and that is all removed. So I tried to remove any trends that I could see that were not solar cycle related, and then you end up with something that looks like this. The other thing that also was observed in the global that is of interest here is that what is not as pronounced, or if I say it more forcefully, you don't see the typical precursor flows. Usually when you look at zonal flow or meridional flow, and before this new cycle appears in the magnetograms, etc., a couple of years before, 2-3 years before, you can see it already in the flow patterns. But you do not see this precursor or not much of it in the radial gradient. And the other thing is, in the flows, you also see a poleward branch where the sort of one thing goes to the equator and the other one goes to the poles. And that is not really visible here either. I mean, there might be hints, there might not be, and part of it might be the noise. So, but and the global ones don't see it either. But let's, for the sake of argument, if it's not there, what that could mean is like the paper Kitiashvili in 2016, what if the radial gradient is only weakly sensitive to the magnetic fields? Then what this would imply is that if you would see it only if the flux is above a certain strength, and if it's below that, you just don't see that. And so it could very well be that this might mean you have to have a kilogauss or more where the activity is, but at the locations higher to the pole and in the precursor part where the stuff sort of bubbles up, the flux is just less than that threshold. And the last slide that I have is, this is just sort of again, take one latitude and sort of compare the different measurements. And here it's the black is the Gong, blue is HMI, and the red is the big tile HMI. And so you see, yes, while the values can be different, quite different, the solar cycle variation is the same. And so from the bottom at the 0.96-ish, it still is anti-correlated with a flux, which is what the global results show as well. So this all sort of hangs together at this point. So the summary out of all the stuff that I've been talking. So yes, if you say, what is the radial gradient? What value is it? The log, then at 0.99, close to the surface, it is -1. But it is a little bit steeper close to the surface. But is it steep enough to be -2? Well, we'll find out, I guess. And then what that may or may not imply is there an upper or lower near surface shear layer? Again, and the radial gradient, yeah, there's a variation with the solar cycle. Clearly it's there. But it seems, if you say the precursor and the poleward branches, they're not really that noticeable. So maybe what they indicate, presence or absence of activity, or maybe above or below a certain threshold of flux. And the extent of the near surface shear layer is deeper at the equator, shallower at mid latitudes, and is also shallower at locations of high magnetic activity. Now, what does that imply? So, and with that, I'm done. Stunned silence.
Well, thank you, Rudi. Is anyone? Okay, I see we've got a hand up from Paul Rajagur. We'll start with him.
Yeah, hi. I just had a question about in one of the slides, Rudi mentioned that the sun has it easy to have a shear layer near the equator than at the higher latitudes.
Right.
So I'm just wondering, the understanding that rotation, the transition from rotational influence to otherwise is the one which defines the shear layer. Since the equator rotates fast, maybe the rotation should extend little higher, opposite of what we expect, or opposite of what you showed. I mean, I'm just, I don't know. I'm just just curious why it is it's deeper at the equator than at the pole. So if rotation actually is the main deciding force, which makes a transition from rotational influence to non-rotational influence, which Nick mentioned in his introductory remarks, then we would expect the other way, right? Anyway, I mean, it's just a thought.
Yeah, I'm not sure what, because I was just when Nick pointed out, the models find it easier to create a near surface shear layer at the equator, and I said, wait a minute, isn't that what that paper shows, that it's a little bit deep? So, but I'm not sure. I guess that it would be a good question for people to think about. What does it mean? I saw Sasha and Yuri having their hands up, so Sasha.
Hi, Rudi. Thanks for the very interesting presentation. I have a question. When you discuss variations with solar cycles, of course, there is effect of active regions. There are some inflows active regions and circulation around active regions. So have you looked separately at active regions, or how you maybe mask active regions? Because where is the solar cycle effect and where is the local effect of active regions? Right.
I mean, that is a good point, because with the flow, I have not tried. I mean, I personally have not tried it with a radial gradient, because I take a numerical derivative of noisy data. And so, but yes, that would be something to try with the flows like the Murnau flow or the zonal, especially with the Murnau flow. That's more obvious, because the locations of activity have these inflows, right? I mean, we know that, and we have measured. I tried to separate that into sort of active and quiet regions, and yes, there. And I think before that, I mean, Irina was the first one, I think, who tried that with rings. And yes, it's basically even if you remove the effect of the active regions as such, if you try to mask them out, there is still that kind of inflow is there. It's just diminished in amplitude, but there is something there. So that is a very good question. So it looks almost as if you have two separate effects, like you have maybe this is the near surface cooling effect, like Hank Sprout had advocated, that is what this is, and that is what you see as the effect of the active regions. But there is an underlying inflow, which is probably the rest of the magnetic field that might be there, and you just don't see as active regions at the surface. I do not know. I'm just making this up. I'm flapping my hands here. So
yeah, perhaps one way to distinguish is to average your active regions, separately, consider separately, and then compare with the mean, right?
Yes. That exactly would be the thing to do. I think because that would be the thing to do, to separately average over active regions and quiet ones. Because what I've done with the flows is, these kind of super synoptic maps, what they are, you take daily flow maps, organize them in synoptic maps, and then average over that. And so what one can do is take a synoptic map and then mask out, let's say, all the active regions, or mask out all the quiet regions. So make two subsets, one active, one quiet, and try to be not blah blah blah, and then do it again. And so yes, that is something I could try. And yeah, Yuri, I think you were next, and then Jörn. I saw Jörn's hand too.
Thank you, Rudi. Could you comment on what assessments have you made about possible systematic uncertainties that arise from ring diagram method?
Oh,
in particular, are in size of the
sorry, can you repeat that? At my end, it just broke up.
Same here.
Oh, well, let me try again. Could you comment on what assessments have you made of the possible sources of error as they enter into the ring diagram methods, particularly with regard to the tile sizes that are being used, overlap, and things like that? I mean, it's fine to say, you know, we have some boilerplate machinery that really is strong, but do you see some possible confusions, particularly a little bit in the spirit of what Sasha also asked, of crosstalk with magnetism in different ways, for instance?
Sure. Yeah. I mean, we know that we have these kind of center to limb effects, right? I mean, like Jean Wei and Raju have seen in the time distance. I mean, we know that that is something I have sort of a correction. These things are correct for what that means is like rotation. Somehow the east and the west rotate at different. I mean, you have, depend on which side of the center to limb you sit, you get different values, but you also get that in the north-south. So those kind of things I try to correct out. This is some other things is like the geometry. So you can see if you go to away from this center is always fine, but if you go away, then simply because you have a sphere that you project onto a plane, and then you have an atmosphere in that sphere, so you mess with a anyway. And just the simple geometry will do something to you because your pixel cover then other areas, and so the resolution goes down as you go to the limb. And so that is something that will affect Gong more than HMI, simply because of the spatial resolution. So that is where some of these things at high latitudes come from. And other things, I mean, they're in the respective pipelines, they take care of the usual projection and imaging and those kind of things that are, yeah, I take what they provide, but the different patches, remember the grid is about half the patch diameter. So that means every other, if you skip one patch, let's say 0 and 15, they're independent, but 0 and 7.5 are not, simply because they overlap. But since these are circular appetized one, it's actually not as bad as one might think. I figured it out one time, and so in that sense, even neighboring ones are not as dependent as one might think, because you say 15 degrees, 7.5 degrees spaced, it's just right. So no, because it's a circular appetization, it's not as bad as one might think. So and I haven't done it recently. That's one on the to-do list for the future, is in about before HMI got going, there was comparisons between the global rotation rates and the ring results. That was done by Sabani, and another one was done by Rachel Howe and Sabani Basu. And then they found that they agree reasonably well. Okay, so but still, you cannot preclude that activity might do some. I mean, let's rephrase it carefully, because there's been some confusion about that too. The activity, of course, will influence it, but because rings in general are fairly broad patches, and what you want to go for is flow. So you look for in that sense a difference, right? And so that is easier than the people who try structure inversions and try to get that out of it. That's where it's much harder, because you need a reference that for the quiet sun, etc. So there are all these kind of tricky things, yes, but overall I think they're fairly all the comparisons so far show that it's fairly reliable, and yes, there are differences in it. I mean, don't get me going on more of these things, because I did not emphasize that either. In the zonal flows, you can see they're sort of this, depending on what you compare. If you look at the plot, you can see that between HMI and the Gong ring diagram results, there is sort of a 2 meters per second difference. It's an offset between the two, and it varies, but I have no idea where that comes from, okay? And you say, well, that's pretty big, because I'm showing it on plots of 20 meters per second. However, if you show this to somebody else and add the rotation rate, which is about 2,000 meters per second on top of it, then you say,
then you see almost nothing.
So don't get me going on systematics.
Right.
Otherwise, we talk, the rest of the day is gone. I
Thank you.
hope that helps. I hope I explained some of the things that, but yes, yeah. I hope that helps some. Jörn, I think you were next, and then David.
Yeah, I have just two small comments. So to the first question, I think it's very interesting that the near-surface shear layer is the thickest near the equator, because when you do global dynamo simulations, you normally end up easily getting a near-surface shear layer at the equator. Doing it at high latitude, it's the very difficult part. So maybe these are actually related. So that's an interesting point. Then I wanted to comment on what Sasha may be saying. As I think this anti-correlation, what people find in helioseismology with the cycle. I mean, there have been some nice paper by Kitiashvili who try to explain this. And in short, it is like this: that the quenching of the turbulent viscosity is stronger than the quenching of the generating part of it. That's why you get an anti-correlation. That could easily, of course, change if you go then to deeper layers. So what I think helioseismology find is actually very well in agreement with this model. So that might be actually correct.
Yeah, because not knowing anything about models, I always latch onto the ones that seem to agree with what I find, right? So this is nice. Thank you. David?
All right, may I? Yeah. First of all, Rudi, thanks for a really good start. I'd just like to remind us all that simple physics says that conservation of angular momentum by inward flowing things that Gilman and Foucault talked about is certainly the major part of this, but it doesn't conserve because there are fluid flows with pressure fields that adjust, and as the effects of rotation come further in, there's more adjustment so that you get away from that. And so the interesting thing is, the -1 that probably comes just from hydrodynamics, the convection and the response of the convection to the effects of rotation. The really interesting part to me is the effects of the magnetic fields and how they come into making it -1 and changing it from -1. And I think you showed some very interesting results there that, if I get it right, it looked like where the active regions were, at least deeper down into the layer, it made that logarithmic gradient more negative. Is that correct? And so that should tell us something about the mechanics that's going on here. So I'd certainly like to see more of that. Thank you very much.
Okay, well, thank you, Rudi, and thank you, everyone else for the great questions and discussion. Why don't we move on? I believe that Paul Rajaguru and Junwei Zhao are going to present a few slides to keep the discussion going.
Yeah, hi. Okay, let me just, I have a few slides to share. Let me just show that. I hope you see my screen. So I suggested this topic of discussing the changes in the flows, near surface flows in the near surface shear layer. So I just quickly say a few words about what I think is important. It just personally, maybe it's a lot of bias from my personal understanding. So yeah, feel free to ask questions and yeah, this is anyway open discussion. So the NSSL is defined by the rotation rate, which has characteristic latitudinal structure, similar to zonal flows, which we just saw from Rudi's talk, basically the Antia-Basu results. So almost all known changes in the rotation and meridional flows are related to the active region magnetic fields. So the question is that studying the dynamics of such flows may reveal clues on the maintenance of the shear layer. I mean, that is the main motivation for studying the changes in the near surface flows. And the questions are, what causes the changes? And I'll show a few slides on these examples. Active region inflows, which we all know is understood to be thermally driven. They appear to define the changes in the meridional flows. But the question is that all to the changes which we see? And the relative magnitudes of direct magnetic effects like Lorentz force and Maxwell stress, and the flows which are thermally driven. So these are the questions I think are important in the context of what we are discussing. So let me just show this slide where I just on the top is the what we just heard from Rudi. This is the changes in the radial gradient of rotation rate at the surface at 0.99. We see the active region belt coincides with the slower gradient, smaller gradient, the blue and purple region. Whereas if you correlate that with the zonal flows, for zonal flows, I just took the slide from the results from Junwei, which is available at the JSOC website. It's from time distance helioseismology. I chose time distance because we can see north-south asymmetries in the flows. Whereas the global seismology always shows the symmetrized structure of the flows. So there's a very nice coincidence of location being the zonal flow location, the faster flow coincides with the near surface gradient being smaller, the rotation gradient. And for the meridional flows, we all know that there is this what is shown here is the red is a poleward flow. In each hemisphere, red is a poleward. So in the north, red means pole towards the north, flow towards the north. And the red in the bottom southern hemisphere means flows towards the south. So there are these inflows towards the active regions, which characterize the changes in meridional flow as a function of solar cycle. So so understanding the origin of these flows should definitely help us understand the processes behind the maintenance of near surface shear layer. So that is the main point I wanted to raise. And as Rudi mentioned that this changes, the rotation gradient changes in depth, whereas at 0.95 it's the opposite. The gradient is larger at the locations of sunspots. So that's another interesting point to understand. And one more point I just wanted to talk about is this changes in meridional flow basically correlates very well with the magnetic flux. So what I have plotted here is the curves at the bottom panel are the cross equator flows, which you see as changes in meridional flow. Is correlated very well with the magnetic flux, which is basically the north-south asymmetry in the magnetic flux, which you see on the right. So the negative cross-equator flow means flow towards the south. That's all I wanted to show. I think Junwei has the next few slides, which I have, he will talk about. Junwei, are you there?
Yeah, I am.
Okay. Yeah, this your slide. Yeah.
Right. So this is basically is also very similar to what we showed on our GSOC website. But on the website, we only show the first 60 degrees in latitudes. But now, actually, we have data available up to at least 80 degrees. What's shown here is within 80 degrees. These are the zonal flows during the HMI period from 2010 to just last month. Next slide. Yeah, so since we have 12.5 years of HMI, we can compare the current cycle 25 phase, early rising phase with the rising phase of cycle 24. So what are highlighted here are the zonal flows in the higher latitudes. What's in the box is between roughly 40 degrees to 65 degrees. If we compare this to the high latitude, north 50 degrees, for example, north 50 degrees, in 2010 to 2011, with 2021 to 2022, we can easily find that the solar rotation at this latitude slows down dramatically. When I say dramatically, it's not very big in the flow field, in the flow speed. Is roughly, I think the speed change is about 2 to 3 meters per second. So if we recall that cycle 24, comparing with cycle 23, the high latitude rotation speed already drops by something like 3 meters per second. So it looks like cycle 25, at least for the rising phase, also drops nearly 3 meters per second compared with cycle 24. 25 is 3 meters per second slower than 24. So this is one significant change. We will continue to monitor what's going to happen next. Next slide. So the previous slide was higher latitude. This one, let's look at just the lower latitude around the solar equator. This is where the torsion oscillation, the equator-ward torsion oscillation is often very clear. If we compare the cycle 25 with cycle 24, we can find that the torsion oscillation became stronger than the previous cycle by roughly 1 meter per second. Okay, so next slide. Since we have slightly longer than one solar cycle, we can look at the equator-ward branch in total for cycle 24. Cycle 25, I should say. So it looks like the equator-ward branch started around 2013 and continues. It still continues towards the maximum of 25. But what's noticeable is that between 2015 and 2017, roughly in 2 years, this branch seems broken. It's not very consistent in our results. So yeah, I think these are all the just a few things I want to mention in our analysis. We will continue to monitor the evolution of these results.
Okay.
Yeah, so it's open discussion. Yeah. So.
Yeah, exactly. I was just going to say, any questions or comments on what Paul or Junwei have presented? I see a hand from Sasha.
Hi, Nick. I have some comments, concerning this what Paul and Jinwei showed. If I can share my slides.
Yeah, sure.
So what I just present some what we do in Dynamo team. So by the way, we have a Dynamo team in COFFIES, and if you haven't joined, then please join Dynamo team. Send email to me or share to participate in Dynamo team. So I'd like to draw some attention also for global helix seismology. It also looking at variations of particular the torsion oscillations. We call torsion oscillations are very important. And this shows for some previous data, this combination of MDI and HMI, and we can trace the subsurface zonal flows also through the whole convection zone. And here that's a feature that what Jinwei mentioned, it is extended solar cycle, which is quite important for understanding the dynamo. It's in torsion oscillations. And we look a bit differently at the gradients. So instead of looking at the velocities, we look at the acceleration, because acceleration is what explains driving essentially. That we can relate to various forces acceleration. So the differentiating time, not in radius, but differentiating time, that the measurements of angular velocity from global helix seismology. And if you overlay with magnetic field, then you can see that regions of magnetic field, both in active latitudes and in polar regions, they coincide with zonal deceleration. So it's quite interesting. So then we decided to look at the zonal deceleration through the whole convection zone. And I show this movie that reveals it's a movie of the zonal acceleration as a function of time, different frames at different times, 72-day cadence on this movie since 1996. And you can see the vertical cut through the whole convection zone. So this is from global helix seismology. So the blue here is deceleration and red is acceleration. And if I play this movie, you can see migration of zonal acceleration, which relates to some forcing inside the sun. And here you can notice that migration near the surface. And we know already from surface measurements that where we have a blue, it's near the surface coincides with magnetic field. So we can see here how distinct this migration of zonal deceleration in the subsurface shear layer. So it obviously plays some role in solar dynamo. So it, again, this then I did some tracking of this. This is not velocity, it's a tracking of these patterns of acceleration, deceleration, and we can actually see in the origin of the following solar cycle when the current solar cycle is continuous, is somewhere at the bottom of the convection zone at high latitudes. And but we develop a model. We also, it's in the team, we develop a model. And this is a simulation similar. This is a full inelastic equations similar to what Nick was showing, except that it's formulated in mean field theory. So it takes into account interaction between small scale turbulence and large scale flows. So it was previously 2D. Now it's developed, Larry Pippin developed to 3D. So it takes into account all equations, all MHD equations and heat transport. And it explains, actually, this model explains torsion oscillations. It explains also the differential rotations of the shear layer. So here on the image that it shows here, that on the top right, you see the comparison of the model with two different models. It shows in blue and red, and the black shows comparison with HMI. So the model does reproduce the super shear layer as well as differential rotation. This is mostly due to lambda, it's called lambda effect. This is non-diffusive angular momentum transport with because of interaction of turbulence with rotation. So then so it's again, these are movies of this, and we can also compare with zonal acceleration movie. And we can see similar patterns, at least qualitatively, we can see similar patterns of migration. And also you can notice in Leptocline, maybe for the next meeting, that interesting migration in Leptocline that this model shows. And what is interesting, this model it explains the extended solar cycle. And the main reason for this is, as Paul mentioned, it's an effect of magnetic field on the heat transport. It's not direct effect of magnetic field. But what's interesting, the model predicted also extended solar cycle for meridional circulation. And it showed that that convergent flows towards the activity belts. Also in this model, this was in this stage, it was two-dimensional, was known flows towards the active regions. And that we compared, then we did some analysis of the data that Junwei showed, but we look at meridional flow at this data. That's HMI data, time distance diagram. And indeed, here at the bottom, at the top, you can see the magnetic butterfly diagram. At the bottom, that meridional flows calculated, east-west flows calculated from the time distance diagram. And here that we didn't reverse sign across the meridional circulation. So it's from south to north flow. You can see change of sign across the equator. And here that what's interesting that the meridional circulation, and since 1916 was 15 was solar minimum, so it's still since 2018 it was solar minimum, and you can see that meridional circulation variation of meridional circulation continue through solar minimum, so it's not completely effect of magnetic field. But during solar maximum, like in 2014, 2015, we can see enhanced variations. And this was the effect of what we believe it's a convergent flows around active regions. And here you can notice this cross-equatorial flows, but they probably just related to the active region. So what I think that what we see some of the solar cycle variations, especially it also a significant part of this, it's a local effect of flows around active regions. So these inflows, they can cross the equator and then be displaced on this as a trans-equatorial meridional circulation. Okay, that's all I wanted to say. Thank you.
Thanks. I see that Roger has his hand up.
Right. I could share my screen at some point.
Yeah, feel free to share your screen.
Okay. Yeah, well, I couldn't while somebody else was sharing their screen, so.
Oh, okay.
So I have this PowerPoint that, oops, I'm not quite sure I did that right.
We can see it.
You can see it? Okay, well, so I'll do a slideshow. So I have, you're seeing this, I hope, the torsional oscillation plot from the solar surface.
We see it, but we see the presenter view, which is probably okay, but.
Okay, so what do I do? Stop sharing and try sharing it again? I don't know. You see, I
think your figures are large enough that it's fine. I wouldn't worry too much about it.
Okay, so I'll go back to the first slide. Okay, so I've stopped it, so I'll do slideshow again. Maybe it'll beginning. Are you still seeing the presenter screen, or am I starting off? Okay, well, anyhow, what I have here is a new rendition of the torsional oscillations, where I've used a couple of new procedures to correct for the effects of magnetic fields on the Doppler velocity, and also correct out the long-term averages. So this is a almost 29-year average of the rotation rate on the left here, and it's somewhat complicated. It has a high rotation rate in the southern hemisphere compared to the northern hemisphere, and if I don't take that out, then the rapid rotation in the south kind of dominates everything and distorts what you're seeing. If I do subtract this long-term average from the individual years, then you see a really quite nice torsional oscillation plot. And I'll note that in the speed up and slow down, there is a semi-gap in the slowdown, but it's not too prominent. It's kind of becomes a bit mushy. But the speed up pattern extends all the way from the poles towards the equator. The place where the long-term speed up winds up was in the north in the early 90s and in the south in the early 2000s. So this pattern is asymmetric relative to the equator. And also the loop back that you see in the deeper torsional oscillations that are gotten from helioseismology inversions does not seem to be happening in the high latitudes at the surface. The degree to which I go towards the poles on this is a little bit lower than what you would have with helioseismology. So there's a possibility that as I extend this to higher latitudes, I may see the loop, the switchback that you see in the helioseismology results. This is a comparison between my torsional oscillations and Rachel Howe and company's torsional oscillations for one 10-year period. I don't have the data for newer times because our equipment stopped working in 2013, so we don't have any extension of the time period beyond that. The latitudes that correspond are indicated by these little blue lines. So you can see that my highest latitudes are not quite as high as you have with the helioseismology. And it's possible that if I extend this upward, it will curve back towards the future, the way you see in the interior helioseismology results. But I don't see any breaks in the speed up pattern. Maybe there's occasional breaks in one hemisphere or the other, but generally they continue on. And then I wanted to show this, which is the meridional circulation, which I get by subtracting the east-west meridian, the east-west limb shift from the north-south limb shift. We have this limb shift phenomenon produced by the correlation between the temperature of the convection cells that are reaching the surface in the granulation and their velocity. They tend to be coming, the upward motions tend to be weighted more heavily, and that produces this limb shift function. By deriving the limb shift function from the east-west, we don't have any meridional flow influencing it. And so I subtract that from the north-south limb shift function. The equator is kind of a jumble. I don't really believe that the equator is downflowing, but it might be. I don't think we have any evidence of it. But I do believe the upwelling at the 3 solar minima, where the flow reverses at the polar region. So it's instead of going down, flowing towards the poles and descending at the poles, the material is coming up and flowing out from the poles, both in the north and the south. And for these 3 successive solar minima, the minima are not equally spaced in time, but the correlation between the upwelling from the poles and the time of solar sunspot minimum is related. So that's, these three things are the slides I wanted to show, and I'm willing to listen to comments and questions. So leave it open for the group to respond.
Okay, well, thank you. David Hathaway's had his hand up for a while, and I'm wondering if his comment might actually be on something previous.
Yes, on previous, more to the point about the meridional flow that we heard about in the talks prior to Rogers. The inflows towards active regions and as well as the cross equator flow seems to be near the top of the surface shear layer. That Lisa and I have been measuring the motion of the magnetic network with our MagTrack program for some time. It represents a depth about midway through the surface shear layer, so 25 megameters depth or so. And at that depth, we do not see inflows towards active regions. We see a weakening of the meridional flow, but not towards the active latitudes. And the cross equator flow, if anything, it seems to be, rather than away from the active hemisphere, it seems to be towards the active hemisphere. So just a cautionary note that these variations in the flows are a function of depth through the layer, and again, a lot what we heard from local helioseismology is much nearer the surface than where we look in the middle of the shear layer. Thank you.
Okay, and I saw Irina had her hand up, I think.
Yes, I just start thinking what I have maybe too many questions. I have question to Junwei in particular. When Junwei, you show your torsion oscillation map, it looks like flows for solar cycle 25 is stronger than previous cycle. Is it mean what we are expecting cycle to end soon?
I don't know. I don't have any answer to this question. I'm just simply showing what I saw, what we saw from our results. I don't want to indicate anything further than that.
I have question to Sasha regarding subsurface shear layer. What kind of background model was imposed to get subsurface shear layer? Because we know for global simulations it is kind of very tricky to get a sharp gradient near a surface.
I mean, for the measurements, yeah. So what we didn't that usually when look at torsion oscillations, you have to subtract because image differential rotation, and then the pattern depends a lot on what you subtract the mean rotation. So that's one of the reasons why we look at the zonal acceleration, because then it's independent of what is the background rotation is. And in terms of I'm not sure that what you're asking about.
My question was in model what you presented, and it
in the
looks
model,
like
yeah, the model
reproduce subsurface shear layer. And my question is, what difference from previous models?
It's old model essentially that was developed by Rudi Kitiashvili. They showed this. It's you have to include what's called that lambda effect, and then also include anisotropy of lambda effect because due to the certification. And this is interaction between rotation and turbulence. There are some 3 different mechanisms of angular momentum transport. It's just meridional flows, and then diffusion, and this what is called interaction with turbulence. It's a lambda effect. So that explains it's a lambda effect, but it was that kind of standard result of mean field theory. And the global simulations that are currently performed, they're trying to reproduce these, but probably what's missing is interaction with turbulence. So the turbulence is not completely resolved in global simulations.
Okay, and I have a very last question, I promise, so, to Roger now about torsion oscillations, what you showed. What I notice in your map, torsion oscillations probably a bit shifted from equatorial area. Can you explain this?
No, I don't really know why the shifts are there. It's just what comes out of the analysis. The data that I've shown here is post 1983. The 1967 to 1983 data has a problem with the calibration of the speed, which causes the global rotation rate to go up and down inversely proportional to the calibration coefficient. So the product of the two is more stable than the individual rotation rates. I don't think it influences the torsional oscillations, but it does cause me to worry about that. So I haven't gone back before 1983 at the present time, but I plan to do that as soon as I can. But as far as why the curve and the average rotation rate has the shape it does, I don't really have an explanation for that. It could be instrumental. There are a lot of things that could happen as the Doppler shifts are analyzed. So I don't really know. And subtracting it makes a nice diagram, and 30 years is enough to mostly eliminate the temporal dependence of the calibration coefficients if they are still present. So not sure that helps, but that's what I have.
Okay, thank you.
So we have David, and then Rudi, and then me.
Yeah. Okay, I have a comment related to Irina's question with Sasha relating to producing the surface shear layer with models. Of course, the difficulty with 3D numerical models is that you don't get right to the surface, and the surface where convection is driven and this happens is critical in doing it. So I think that's the difficulty in the numerical models. The model that Sasha and Pippin has is a model in which you prescribe a stress tensor is a function of depth and latitude, and it's that stress tensor, the lambda effect, as Sasha called it, that produces it. So they can produce a shear layer within their model by tailoring that stress tensor to represent the change in those stresses with depth. So just to comment on that and the general idea of how do you make these with models.
Okay, is it my turn now?
Yes.
If nobody wants to comment on Dave's comment. With regard to the Roger's results that it's sort of a bit offset, I just want to relate to two things that are noticed in the rings. The one thing is that sometimes the rotation rate, they depend on whether it's an activity related effect, right? I mean, that can happen is that during cycle 23, the activity is predominantly in the southern hemisphere, and so you get an asymmetry in the zonal flows between the north-south. However, on top of that, there seems to be some other north-south gradient in the zonal flow on top of that, which I attribute largely to the center to limb effect. But there can also be, there might even be some real sun-related thing on top of it. So I'm just adding that to the commentary that maybe maybe it's something like that, that it's either active region related, or is it an artifact, or some other not. I mean, if you have a gradient in your things, it will do that. It might do that too, right? So it's just that kind of. To the cross-equatorial flow that we've been talking about, that one you see in the rings as well. You see something that if you do these supersynoptic maps over a solar cycle, it's something of the order meter per second. It's very small, but it's there. It's persistent. And the way I see it is as the others have said, you have an inflow towards active regions, and so the flow goes towards the hemisphere that has more activity than the other. And again, close to the surface, as Dave said, and as others have commented on, this is depth dependent. You have to be careful what depth, when I make these general statements, please question me, what depth did I mean, right? So otherwise it can be different. And so there it seems like, yes, there is a flow towards a cross-vectorial flow, small, that goes more into the hemisphere with excess activity. And then when that sort of goes away, the rest of the cycle, it still goes into that hemisphere, even though now there's no more activity on the surface, but it's just a quiet sun, but it's diminished, it goes into zero, the new cycle starts, and it goes in the other direction. I mean, that's what I saw between 23 and 24. So then the one, because 24, remember, activity first appeared in the northern hemisphere, and so all of a sudden the cross-equatorial flow goes to the north. So yeah, so it seems activity related, but there seemed to be also some, for better word, an inertia in the flow. When it's going, even if the activity, the cause of it disappears, it might still go on a little bit till it gets jolted in the other direction. And again, this is near surface. That's it.
Before any other comments, including my own, Irina, I just want to make sure that you are okay on the time, that if we continue to talk for another 10 minutes or so, it's not a big deal.
Yes, sure. Yes,
Okay.
it is important to keep discussion going if you have discussion.
So I had a comment and question on the high latitude countercell, but I wonder if Sushant's comment or question is more relevant to what Rudi was just speaking about.
I just wanted to mention Jeff Kuhn and his graduate student Ian's work on using the Poynting Robertson drag or photon breaking to explain the existence of the near surface shear layer. And I just wanted to pose this question to the people present here. In our past discussions on the near surface shear layer, I've never heard anybody discuss this as one of the causes for the near surface shear layer. Is it because people don't believe in it, or just haven't looked into using the Poynting Robertson drag effect to explain the near surface shear layer?
Well, I can say that this is new to me. I'll have to look at this.
No, so as I understand the explanation, they require no mixing of the angular momentum from the near surface shear layer into the bulk of the convection zone over the lifetime of the sun. So I find that implausible, considerably implausible. So the effect, of course, is if you have rotation, then the frequency of the electric photons depends upon whether you're looking at the prograde or the retrograde side. But it's a very small effect, and to go to account for the near surface shear layer, they assume that there's no mixing of the angular momentum across the near surface shear layer in the lifetime of the sun. So I don't think this is plausible.
Okay, thank you for that, Robert.
Great. Roger, I was wondering if you could put your plot back up with the high latitude counter cell in the meridional flow. Oh, you're muted.
Roger.
I don't think I can unmute him unless it's just me.
That would be sneaky if you could unmute as the host.
No, okay, so let me try this again.
Oh, there we go. Yes, we hear you now.
Yeah, I was muted. I'm sorry. My wife got home and is talking on. Is this the plot that you wanted to see, or can you see it? Or
We see your desktop and not the plot. But it was your third slide, I believe.
okay, so this one. Can you see that now?
Yeah, that's right.
Yeah.
Okay. Yeah.
So the way to read the blue is that's an upwelling in the polar regions. Is that correct?
Yes, that's it's coming towards the observer. It's blue shifted instead of red shifted. So the meridional flow throughout most of the zone is towards the poles, but then at these 3 times near sunspot minimum, the surface flow is away from the poles. And I presume that material is coming from somewhere. And the only somewhere that's really available is from upward motion at the poles. We've all been assuming that there's downward motion when the material is flowing towards the poles. So I'm just changing the sign and saying, well, if there's downward flow at that normal time, then this must correspond to an upward flow. So I call it an upwelling.
So my question here is first for Lisa Upton, and then for any of the mean field modelers, maybe Sasha Kosovachev. So it's kind of 2 parts. I guess one is, does this correlate with, I know you've been presenting some evidence of high latitude counter cells kind of appearing and disappearing over the solar cycle. Lisa, does this correlate? Does the timing of this correlate with what you've been showing, like what you showed this summer?
Yeah, Nick, I think we need to look closer at this. And I'm wondering, Roger, if you can subtract mean meridional flow, then because the model predicted that you can see extended solar cycle variations in the meridional circulation. And if you subtract the mean meridional flow, I wonder if you can see something similar to what you see in the top picture, torsion oscillations. Have you tried this?
If you just take a plot of meridional flow velocity versus time at specific latitudes, then you do see a very strong dip at these times. I think that's comparable to what you're suggesting I do. And yes, I've made those plots, but I thought this global rendition was interesting because it shows the 2 polar regions simultaneously. Did I just change my slide? I must have.
Yep.
Yeah, you did. Yeah.
I didn't plan to. Sometimes the mouse does funny things. So yeah, I have some of those plots and I have error bars on those time or velocity versus time plots at specific latitude bands. So you can see those things, and you can tell that there is a variation even in the speed of the flow at the lower latitudes. You head towards where the magnetic fields are present. So yeah, they're somewhat interesting, but at the equatorial regions, I'm not quite sure what to make of it.
Yeah, here-
well, oh, go ahead, Sasha.
Here's what's interesting, that if you look at your images, we can see, yeah, sorry, I think it was interesting what I asked this, because we can see correlation of these counter cells with torsion oscillations at high latitudes. It's a kind of a start of this extended solar cycle.
Well,
So-
yes, that's certainly one of the things that caught my attention, but of course, this is related to the switchback effect that you see at greater depths, where the flow pattern goes towards later times. So the correspondence that you can draw between the upwelling and the slowdown of the rotation rate, which is both the north and the south poles have that in this diagram. If you put the switchback effect in, then that correspondence disappears. So I have been trying to get the higher latitudes out of my data. Our spatial resolution is not as good as the spacecraft spatial resolution, so it's a challenge. And I got to about a week from in the past and decided I had to stop working on that if I was going to prepare presentations. So I have dropped that effort for the last week and a half now. But I will get back to it now that we're through with these presentations.
Yeah, that's something that we need to look more carefully at. This certainly is an important issue. Also, Genway showed interesting results at high latitudes, and I believe that Genway also has meridian flows also at high latitudes. So maybe we should kind of look at this topic and from various perspectives.
It's
Yes,
possible that there's a depth dependence.
Let's let Lisa talk for just a second.
So Nick, I think you were asking, and correct me if I'm wrong, I think you were asking if these are consistent with the counter cells that David and I see in our analysis, and when we're seeing the high latitude counter cells in our meridional flow measurements. And the answer is no, actually they're not.
Can I ask anybody who's not Lisa to mute?
I'm on it.
So actually, there actually are some pretty interesting differences, so one of the things that the biggest difference is that we in solar cycle, in the previous solar cycle 23, we saw a significant asymmetry in the counter cells. Between 95 and about 2000, we saw the counter cell in the south, but we didn't see any in the north. And then at about 2000, the one in the south turned off and the one in the north came on and was persistent through the end of the cycle to 2010. And then both of them disappeared at about 2010, at the beginning of cycle 24, and we didn't see any signature of them until about solar cycle maximum, 2015 or so. And then we start to see signatures of them both in the northern and southern hemisphere. This led us to think originally that they were possibly just an artifact of the MDI data, but now that we've seen them return, we're starting to believe that actually these are real structures. And one of the things that I'm wondering if maybe the reason why we're seeing a difference between where we're seeing the counter cells and where Roger's seeing these counter cells could be related to the depth. Roger, what depths would you say that these measurements are associated with? And I know ours are associated with probably about 25 megameters deep.
These are photospheric, so these lines are in the mid photosphere. I have sodium pairs that I haven't really fully analyzed after 96 that show up at the base of the chromosphere. So that we span basically the full photosphere. The 5250, which these are from, is the sort of neutral line, and it's kind of at lower temperatures. And so anyhow, yeah, they're different depths, but
okay,
all photospheric. that we don't go below tau equals 1 for sure.
So it looks like there is some slight asymmetry between the hemispheres. It looks like overall the northern hemisphere it seems to have a stronger signature than the southern hemisphere, but they do tend to remain in phase with one another. It's interesting. I wonder how that changes with depth. And I think Dave is online. I don't know, Dave, do you have any comments, any thoughts that you want to add?
No, I thought you described our results pretty well, but I would note that we do tend to see the counter cells at minimum, which is what Roger is showing on his.
That's right. Yeah.
So I think in that regard, we kind of agree.
Sure.
So just on that note, going back then to what I was about to ask Sasha, I'm just curious in his cycling mean field model or suite of models, if there's a variation in the high latitude meridional flow that correlates somehow with the torsional oscillations.
Yeah, hi Nick. So certainly we can see variations of. I can share again the slide for meridian circulation in the model. If for the correlations that specifically that we need to overlay here with it overlaid with the toroidal magnetic field on this slide, and but we need to overlay with the torsion oscillations. I have not done this yet, but definitely there are some variations that you can consider as I don't know if it's counter cells, but definitely some significant variations at near polar regions in the model. We have not looked at this carefully, but as I said, that we need to discuss this together with observations.
Thanks. And then Rudi has his hand up.
Yeah, thank you. I find these counter cells at minimum intriguing for the simple reason I sort of see the same kind of thing. Must explain what I see. The helioseismology of the wing pipeline, the general stuff, HMI goes up to 75, okay, 75 degree latitude if the B angle is in favor. And Gong and MDI, they go only to 52.5. Again, that's the center of the 15-degree patch. So what I've done a while back is, well, I don't know anything about the poles, but I would like to. So what do I do is I just fit some polynomial to the meridional flow and enforce that it's 0 at the equator and at the poles, and then just plot the polynomial, right? And so if you do that, then you end up with counter cells during minimum at the latitudes that are conveniently out of reach of observation. So it could really be that there is. It seems like we all seem to see something happen at high latitudes at the poles, and so there could be something like that. So I think this is a good trend. This is something for the discussion later on about other missions that we really want to see the poles.
Rudi, I think it's not just for future mission. We can still probably use HMI data and just to put more patches in over to try to extend this and then to test this. That's what Jinwei is doing now. So we probably also it's something for seismology team that we discussed, that instead of saying time distance 5x5 patches, we do 9x9. And then since this issue is so important, we cannot wait for the next mission to solve this.
I mean, you're right. I mean, there are some things that can be done. Or for example, they have also 5-degree patches that go higher, and one could try to look into them. They don't invert them yet. And so yes, so I think that is all a good effort, like what you said, Jinwei is doing with a high latitude, because there's something very curious, because like I said, I just looked at my plot, the same count, because I had seen it only at 2010, right? Because I had 23, 24, but now that same count in that polynomial expansion, you see the counter cell also now at the beginning of 25. So whatever that means, okay, it just, yeah.
Yeah, also before, I'm sorry
Mm.
that I said, quick comment. Also before, what in Hinodi antenna stack, what we did some heliosysmology observation in polar regions.
Right, it did
And
then,
they're
yes.
perfectly suitable for ring diagrams. Maybe we should look at Hinodi and see what.
Oh, that would be a thought. Yeah. But yeah, just to qualify to my statement here. Of course, what the cynic in me would say, well, what it really means is since the polynomial is fitted to the Murnau flow at lower latitude, what it really shows you is the difference in the Murnau flow between max and min of the solar cycle. And that then conspires to gives you that result in my polynomial. Okay, this is the cynic of me speaking. And the other one says, oh no, it's all real. So pick whichever one you trust.
No, I think Rudi, I think you're right to be skeptical. I think we do need to be careful with these measurements because there certainly are, instrumental effects and orbital effects that do come into play. I do think that there is something there though, because number one, the measurements that David and I are taking we are using an HMI. So we are, when the pole is favorable, we are able to resolve the entire pole. The other thing that I would counter with is to say that that this isn't just an oscillation, an annual signal that we're seeing. This counter cells are appearing on a solar cycle scales, and so the fact that we are seeing them change from minimum to maximum, I think lends credence to the fact that there might be something there. But you're right. If you're just fitting with the polynomials, that could come into play. But also the measurements that David and I are showing, we're actually showing the raw measurements, and we're seeing those counter cells in the raw measurements, not actually the fit, the polynomial fits. So we're seeing in the raw measurements, and we're seeing all the way to the poles with the HMI and MDI, not as well, but with MDI as well.
Yeah, and as Lisa said, the annual variation that one can see in the Murnau flow, that is clearly the B angle. Okay, and that
Right.
has to be taken out.
Okay, so I think we should move on to Irina's talk. It is 5 after 12. We've been going for 2 hours, so that I suspect somebody is going to want to get up for a minute. Why don't we take a 5-minute break and start off with Irina at 10 after? Does that sound reasonable?
Sounds great. Thank you, Nick.
Yep.
Great.
And I do want to just call people's attention to the fact that Shay put a link to a Slack channel in the chat. It looks like a lot of people have joined the Slack, but in case you haven't noticed that, you can follow that link, and it's a little bit easier to chat there than in Zoom.
Yeah, and if anybody needs me to add them using like a different email address, please reach out to me. Not everyone, just me, and give me whatever email account you generally use for Slack, and I'll add you.
Great. And so let's take a 5-minute break now, and then we'll continue with Irina's talk on some simulation work she's done. Okay, Irina, do you want to go ahead and share your screen? If you're back.
Yes, I'm back.
maybe it should have been 10 minutes, not 5. We can wait a couple more minutes on people.
Yeah. People need a little bit more time, probably. Yeah, I just grabbed my coffee.
That's what I had left in the pot was cold, so I was heating it up in the microwave.
Yeah. Okay, just I'm going to share my screen first. Oops, let me turn on camera. Okay, so it looks good.
It
Can you
does.
see my screen?
We do. We see the full PowerPoint, so it doesn't seem to be full screen mode.
It is full screen mode. Okay. Okay, let me.
It's not presenter mode, but it just we could see the options and stuff.
I will do in different ways. It is better now.
Yes.
Okay, good. Just let me know when I can start, because maybe you won't give people a couple.
Yeah, we'll wait till 15 after. That's more like a 10-minute break.
While we're waiting, if I can just comment that just looking at the title of this talk, substructure, the near surface shear layer. My pet peeve is calling it the near surface shear layer, because we have a tachocline. We don't call the tachocline the far surface shear layer. So I think it's a surface shear layer, and I assume Irina is going to tell us about the near of the near surface shear layer. Just a pet peeve. I don't like the superfluous word near that we use for the shear layer at the surface.
Yeah, David, you're right. Actually, it is very confusing, because if I would like to be very precise, I have to call this near surface shear layer, right? But I mean Leptocline. But problem is, because everybody knows what near surface shear layer and mean completely different thing.
Yeah, I think we should blame Yuri for this term.
It's too late.
Yeah,
So.
he introduced, I believe. And I look at this because I was also asking, I was fighting for changing this to subsurface shear layer. Because near is kind of strange here, but then it's appeared in, I believe, in the Boulder group, this term.
Yeah, but we cannot change history, so.
Yeah, it's just like torsion oscillations, right? I mean, it's all these names.
Like, now I start complaining what we use sunspot number as measure of solar cycle. But yeah, I see it as really we should go away from sunspot number, but I cannot change history, so. So, and same for near surface shear layer. So it's it's a bit confusing. I agree.
Top of the convection zone shear layer.
Okay. Sorry, we're basically at 15 after. So Irina is going to share some recent modeling work she has carried out involving the near surface shear layer, and take it away.
Yeah, thank you. First, I want to say thank you for organizing this wonderful workshop. Actually, I really happy see so active and interesting discussion on previous topics. I really appreciate it for this. And in this presentation, I would like to go a little bit to different direction and discuss about Leptocline. And actually, I'm going to discuss about existence fine structure of near-surface shear layer. And I will, yeah, I can change slides. It is a good sign. So, of course, I'm not going to stay a long time on these slides. Everybody knows what differential rotation is and how challenging it model. But actually, for me, and especially my previous questions relate, I have a hard time to understand why we have so much troubles to reproduce not only differential rotation and have kind of trick-out models, but also subsurface shear layer. And I just include as example simulations by Matilsky, and but we actually discussed previously what usually what global models can reproduce just near equatorial area shows subsurface shear layer in simulations. And the question is why it is the case, and I think it is kind of one of key to move to our models to more realistic description of global solar rotation, global reproducing of global solar dynamics. And of course, we have many additional global models like Gustavo doing modeling with EULA code, Andrei Stishko. But again, it is very often it requires do kind of adjustment of background profiles to get results to reproduce subsurface shear layer. And and of course, in previous discussion, we mentioned, in particular, David also mentioned a point what global models cannot actually reproduce in realistic way near surface layers. And but as you all know, with local models, it is a problem to do global simulations. So and the purpose of this talk actually discuss what we can do with this. But before going to this, I already mentioned local models, and of course it is not just my brilliant idea. People keep thinking about this before me. And I would like just mention, for instance, simulations by Barikat, and he and his co-authors did actual series of simulations in local domain with forced turbulence. And but they also neglect effects of stratification. But the advantage of this work, they was able actually to perform simulations for many locations along latitude and also at different depths. But it turns out what actually, if we discuss about subsurface shear layer, similar as global simulations, they see formation of near surface shear layer only in near equatorial region. And to address this, we have we decided to perform simulations with stellar box code. And the idea is to perform simulations just on one patch located on 30 degrees latitude and see what we will get. And it is just a quick description of code. I believe most of you are familiar with this. We use it is fully compressible code. We do very precise calculations of radiative transfer in LT approximation, and we do ray tracing using a feature method in 18 direction, and we use non-ideal equation of state, and we able actually do we include the effects of rotation by applying an F-plane approximation, and also we're able to use different subgrid turbulence model. For simulations, what I'm showing, we use standard subgrid Smagorinsky model. It means we use constant coefficients for whole computational domain. And on this slide, you see just illustration of kind of whole setup, and x-axis is always oriented in direction of solar rotation, and the y-axis oriented to North Pole. And on right, you see just snapshots, how it looks like data at the photosphere in terms of vertical velocities and vertical cut. And the dimensions of this box, as you see it in horizontal direction, it is 80 by 80 megameters. And the in-depth computational domain is extended up to 25 megameters, but from analysis, we excluded the last 5 megameters, and the reason for this because we see boundary conditions related artifacts, and just to be safe, we just exclude these layers. These computations also include 1 megameter of atmosphere. Okay, so and in case, because we have rotation, and actually for data what I will show you today, we perform simulations, a whole run is more than 250 hours long, and for analysis available more than 100 hours. And because it is an extreme long data set, we actually can see rotational splitting in if we plot L-nu diagram, and we actually did work. We actually computed HMI line, so we have this data available. Just send me email about it. But also with help Slava Sadikov, we also computed HMI observables. It's still under analysis now. And advantage of these simulations, we also can look oscillations not just at the photosphere, but because we have information across all layers, we actually can look how change properties of our, for instance, L-nu diagram, different layers of our computational domain. And on the right-hand side, you see actually L-nu diagram, sorry, from -1 megameter below surface, photosphere in middle, and above photosphere on the right. Okay, and first, of course, what we want to see is distribution of kinetic energy with depths, and of course, it is not surprising we see a dramatic decrease energy below 5 megameters. And what is interesting, we actually see energy decrease much slower if we go below 5 or especially 10 megameters. If we do just look turbulence spectra on each individual depths, we see, for instance, in photosphere slope more or less corresponding -7/5, which of course, at this point we can interpret is kind of like Shear-like flows. But if you go to deeper layers, it more corresponds to Kolmogorov slope. And for deeper layers, it is, as you see, power don't decrease very much as we go to deeper layers. But also what is interesting in these simulations, we actually start see some signal which correspond close to supergranular flows. It kind of very encouraging in these simulations and very interesting from my point of view. But of course, we should be very cautious about it. And one of reason for this, it is hydrodynamic simulations, so it is some restrictions there. But what interesting for me, what even in hydrodynamic simulations, we see such signal. And I should mention in these simulations, it is not a very strong signal, it is a weak signal, and sometimes it even disappear. So it probably means in terms of, if we discuss about origin of supergranulation, probably magnetic field just amplify signal of flows. Okay, and first thing what we interesting to see if we impose rotation on our computational domain is to look deviation of our flows from imposed one. And on this slide, you see a kind of differential rotation profile relative to imposed rotation. And actually, it is this profile obtained for 24 hours of data, and vertical bars correspond 1 sigma deviations, standard deviations. And first, we may notice what we have a slowest flow near photosphere, and actually flows accelerate pretty fast, up to 5 megameters. And after this, we can see actual change in slope. Below 10 megameters, it kind of hard to say. It is not so obvious changes, but it is really going around, it getting close to imposed rotation rate. So it kind of first interesting sign what we probably have something interesting in terms of fine structure of near surface shear layer. Next point what I would like to show is kind of meridian flows. First, I would like to have disclaimer, so I will never discuss about meridian circulation. And I encourage everybody when we discuss about simulations in local box, try to avoid term like meridional circulation, because as you understand, we cannot really claim circulation. And we can discuss about flows on scales of computational domain, but it is not circulation. And what is important about this, we actually can see near surface, if we discuss about near surface layers, our flows moving mostly in polar direction, but below 5 megameters. Actually, flows we can see kind of very weak flows in opposite direction, the quarter world. So we actually can see a change, a mean rotation from say 12 meters per second to minus 6.5 meters per second. And below 10 megameters, actually we see additional reverse flow again to poleward direction. And it kind of very interesting because it, in some sense, it reminds us previous observations by Junwei for double cell meridian circulation. But in Junwei's measurements, of course, it was discussion on double cell meridian circulation on a global scale, on scale of whole convection zone. In my case, we are discussing about kind of possibility. I want to be cautious there about possibility double cell flows or potential signature for existence double cell meridian circulation, but in near surface layers. But again, it is kind of because we understand this effect actually relate to visible right now in hydrodynamic simulations, and we know in solar, if we discuss about the sun is never pure hydrodynamic. So it means actually these hydrodynamic simulations probably capture kind of characteristic properties, but of course, if we would like really claim about reverse flows in layers, say 8 megameters below surface, of course, we have to perform MHD simulations to confirm it. But in any way, what is encouraging, actually, what if we compare these simulations with with observations obtained with different techniques, it is plot on right. We see actually very good agreement, of course, quantitative agreement, and we see about same layers we have decreasing in meridian circulation, meridian flows, and all these observations was obtained for different period of time, and with different techniques, say ring diagram analysis, time distance histology. And also what we notice, actually, these results also depends what kind of period of solar activity you take. So if you have a period, if you take observations near solar minimum, we have more prominent decreasing in meridional flows on this particular depths. But it looks like, in general, such dynamics is kind of similar if we compare observations and simulations. But again, existence of this reverse flow, it kind of very point to discussion and actually require more simulations, because and especially it will be important to have high resolution at some point global simulations, because it's hard to say it relate, at least for right now, hard to say is such phenomena relate only mid latitudes, or it is just can be observed everywhere. Okay, so next, what is special about these 10 megameters layers? And actually, what turns out, these signatures actually, as I already mentioned, it indicate what we have kind of very special layer, which cover first 10 megameters below surface. And we call this Leptocline, and actually this term previously was suggested by Gaudier and Jean-Pierre Rezilot in these papers, and from Greek it just leptos just means fine. And our idea in this work actually to look if we have more observational evidence of this phenomenon. And I would like to go a little bit to history, and actually it is maybe one of first papers on helioseismic analysis by Dugna, Roger, and Ed Rhodes. And on a very left, you see very well-known LNU diagram, and actually I like this plot very much because you actually can see what kind of parts of LNU diagram correspond, how they correspond to different depths. And actually in this work, flows differential rotation was measured on the first 20 megameters below surface, with separation in depths about 2 megameters, sorry, and observations was obtained for different days, I would say. And what is interesting about these observations actually show what differential rotation, relative differential rotation actually change quite noticeable, even if we take into account errors below 10 megameters. So it basically means what it probably we have something there, but of course we have more results now, and I'm going to look deeper on slides this. But I would like also mention what these results actually was also tested by imposing numerically just some flows to make sure what these measurements actually make sense. And the test result just you can see test results you can see on the right hand side. And in previous simulations, for example, bearing cut simulations in local domain, it was demonstrated what Reynolds stresses may play a very important role on this. And we decided to look on this. And on the left-hand side, you see off-diagonal Reynolds stresses. And actually, it is not surprising to see strongest variation near photosphere. And the strongest variations, of course, strongest variation in horizontal component. We see it peak roughly around 2 megameters below surface. And actually, it corresponds to bottom of granular layer. More interesting to see in azimuthal plane, it corresponds to Rx component, and actually we see if you go below, say, 4 megameters below surface, Reynolds stress is getting negative, and below 5 megameter it became constant. But if you look on meridional component of Reynolds stresses, Reynolds stresses actually below 5 megameters just stay about constant near zero. What is also interesting if we discuss about horizontal Reynolds stresses, you see some strong variation in horizontal stresses around 10 megameters. So it basically means what we have stronger horizontal fluctuations in these layers. If you look on diagonal component of Reynolds stresses, of course, as expected, we see a dramatic decrease in all diagonal Reynolds stresses, but around 8 megameters below surface, it is some deep and some enhancement in Reynolds stresses. And it is more clearly shows actually if we plot anisotropy parameter equation for this, you can see on bottom. And what it actually say us, if we combine all this information, we actually can see kind of decreasing, sharp decreasing of downflows motion, and all energy mostly going to horizontal energy. And actually, what is actually say us, we have these layers, our leptocline, it is not just some layer, but also it shows what we have kind of weak overshooting layer between more and less stable convective areas. So it kind of, in some sense, it is maybe a shift of paradigm. It is too strong word for this, but we see what we have a weak overshooting even between different layers of convection zone. And to continue our discussion, of course, it's important to mention the Rossby number. And in these simulations, because we, of course, cannot model whole sun, we discussing about the Rossby number only on 30 degrees latitude, and we plot the Rossby number as function of depth. And Rossby number is very high. It is also kind of expected, but it increased dramatically with depth, and we see around depths of 8 megameters, actually slope of Rossby number decreasing, change and decrease of Rossby number is became slower. And also we see, of course, such quite dramatic changes in the length scale below 8 megameters below surface and convective turnover time. And I would like to mention, if we discuss about relative angular momentum, we actually found what angular momentum didn't vary more than 5% during at least last 100 hours of these simulations. And next, what I would like to discuss is about radial distribution of vorticity. And on left plot, you see distribution of vorticity for different components. And for vertical vorticity, it is essentially 0. But for horizontal vorticity components, we see near photosphere, it clearly negative and getting to 0 and still fluctuating in deeper layers. And if you look on radial gradient of local rotation rate, actually it is kind of surprising how much radial gradient for local rotation rate correspond to vorticity component. And you see it's kind of just really, even in small details, it is really surprised me how similar it is. And in the first part of our meeting, we actually discuss about values of on what we expect to have for radial gradient of local rotation rate. And our simulations actually show it is, yes, if we discuss about mean, yes, it is about -1. But actually, this variation change with depth. And for comparison, just to illustrate how it corresponds to previous studies and previous estimation of radial gradient of rotation rate, like Karba and Thompson and also Baricat show like it is -1. If we discuss about more recent paper by Johan Reiter, he found if he apply different inversion technique, he can get different numbers. And you see how it overlap with our simulations. But of course, it is we cannot discuss about one-to-one comparison with these because our simulation shows it vary quite significantly with depth. And also recent studies by Antti and Basu shows for this particular latitude, it is roughly -0.85 on depth 7 megameters. Unfortunately, I cannot make a plot because it in paper by Antti and Basu, they demonstrated variations of this parameter as function of latitude, and I cannot really compare for other latitudes. But I hope we will do this in next work. In terms of thermodynamic structure, it is nice to see if we can see signatures of leptocline layer in, say, in density fluctuations or temperature fluctuations. And actually, as you notice, we have a very strong decrease in density fluctuations in layer about 8 megameters below surface. But also, it is not just such sharp decrease. We see if in more shallow layers, we actually have increasing of RMS fluctuations for density. Below these layers, it can tend to be closer to constant, and RMS fluctuations for density decrease with depth, but not, it's hard to say it is constant, or let's say it is, we see weak decreases with depth. Also, if we discuss about RMS fluctuations of temperature, we see quite noticeable decrease in temperature in same layer. And when we discuss about how corresponds such a leptocline layer, and actually we try to think what origin of this. And what we found quite interesting, what leptocline layer located just exactly on bottom on hydrogen ionization zone. And potentially it can be key formation of this layer in case of rotation. And next, I would like just to illustrate a paper by Johan Reiter. And he developed recently a new method to perform measurements of differential rotation. And right and left plots actually a difference between all of them. It is how many spherical degrees was taken into account. But what our point of interest is marked by a rectangle. And you see, actually, we start see some kind of fine structure near photosphere. And difference in previous similar analysis of differential rotation, when we have just very few points in past, it's actually hard to say if we have something real in these layers or not. But helioseismic analysis actually show what we really have this. But of course, we have to perform simulations on different latitudes and in presence of magnetic field for future. And I would like to conclude this presentation, and I hope I will leave more time for discussion on these results and possible advances and what we need to do. And in conclusion, I would like to mention what our simulations reveal development of radial differential rotation and formation of shallow 10 megameters deep substructure. We call it leptocline. And this leptocline layer associated with steep radial gradient of angular velocity changes in thermodynamic and structural properties. And this leptocline actually can have a very important role in solar activity. Of course, it is speculation, but it looks like it is a very interesting layer for study. And our simulations also shows what we have overshoot layer which separate overshoot layer between leptocline and bottom part of near surface shear layer. And our results actually also demonstrate very good correspondence to existing measurements of meridional flows on this particular latitude. And the simulations show potential existence of reverse flows at depths 5-10 megameters below surface. And reverse flows correspond to bottom of leptocline and hydrogen ionization zone. Yes, and our analysis also show potential existence in the simulations additional convective patterns which correspond to scale, close to scale of supergranulation, about 20 megameters. I'd like to say thank you, everyone, and really happy to continue our discussion.
Great. Thanks, Irina. I have just a quick clarification question. So can you remind us how deep your box was, and is the lower boundary closed, or do you have one of these boundary conditions where flows are kind of allowed to come in through the boundary?
Yeah, in first simulations, simulation box is 25 megameter deep, and bottom boundary is closed for flows, and it creates some numerical effects. And actually, as I mentioned in the beginning, when I start do analysis of different properties, I found what some thermodynamic properties behave very well, say even up to bottom boundary, but some of them not.
Yeah.
And they really show effect of bottom boundary. And the reason why I choose cut for, I decided don't consider any data below 20 megameters, just because below 20 megameters, some parameters start show presence of closed bottom boundary.
Great, thanks. So we've got a question from Nick Brummel first.
Yeah, it was just another clarification. Thanks, Irina. It's a very interesting work. Another clarification. How are you forcing this thing? Does it have a background gradient of some sort, or is it just cooled from the top with a radiative coolant? How's it forced?
It is I cannot say it is forced, because convection developed naturally. But maybe to be more clear, we have initial condition is solar model S, solar standard model, and you are right, we have kind of high temperature at the bottom and low temperature on the upper layer. So in this sense, of course, it is forced.
But you solve the radiative transfer equation, right?
Yes, right. But we have solar background model, so it why I should say it is, yes, it is, we have high temperature in deep layers, yeah. But in very beginning, we usually use very small perturbations in velocities, just to make to allow turbulence develop just a little faster, but
yeah. Christina?
Hi, nice work. It's just, I want to mention that these 10 megameters deep is exactly what we see the sound speed variation below an active region. And I have a paper from 2012 where I use global helioseismology throughout the solar cycle, using high degree modes, that are work that I did with Silver and Korsenik. And this, I see exactly the same change with solar cycle in this, what you are calling the 10 megameters deep. So it's, this is through the solar cycle, right? But it agrees with the change that you show in density and temperature. I think that is relevant. It's a paper from 2012, but I think that's relevant.
Yeah. I definitely should look it. Thank you for mentioning this.
I can show the plot, but there might be more questions. Go ahead.
Yeah, it will be great. Of course, I cannot really claim what because simulations itself is hydrodynamic. So of course, I cannot claim any relevance to active regions, even if I like to do this. So but I was really amazed when I look, say, helioseismic studies, for instance, what Rudi showed earlier today. What actually it looks like sun speed variations happen exactly on same location, and I tend to believe it more. Because reason for this, because I assume for helioseismic analysis, it is a lot averaging applied. So it means local variations in terms of active regions. It is kind of little bit, in some sense, it is not as significant, but of course, MHD simulations have to be performed. Thank you very much for pointing your papers. Yeah, I will look at it.
Other questions or comments? Nick, you have another question?
Yeah, I guess I could ask lots of questions because it's very interesting. I mean, so can you asset? I mean, you have a leptocline, but you also have a near surface shear layer, right? I mean, can you ascertain what is the dominant balance that gives you that, near surface shear layer in zonal differential rotation there? I mean, I think that's the biggest question that everyone here would want to ask, right?
Yeah, I just not sure what I understood question. Can you expand it a little bit?
Well, you have a leptocline inside a sort of near surface shear layer. I mean, your model has a near surface shear layer, right? You have a change in the differential rotation gradient towards the surface.
No. My model didn't have imposed any subsurface shear layer. It basically I have model S developed Krisendalsgaard, and basically it. Development of meridian circulation, it is pure kind of spontaneous, it is uncontrollable, or
yeah, no, that's good. But that's what I'm saying is your model does this spontaneously, right? And that includes the sort of a radial gradient of zonal flows, right? Which you could call a near surface shear layer, and part of that.
Yeah.
You defined your leptocline in terms of the meridional circulation. I'm talking about the zonal flows now. So you have sort of a near surface shear layer spontaneously generated in your thing. I thought I saw a plot that showed that, right? Okay,
yeah.
What's the dynamical balance that creates that?
When you discuss about dynamical balance, you mean Reynolds stresses. So what I just try to understand what.
I think that's what he's asking. How is the angular momentum balance maintained? I think.
Yeah. Okay. Angular momentum. Actually, we check. First, I should mention these simulations near steady state condition, and we check angular momentum. It doesn't vary more than 5% for last more than 100 hours. And but I should also mention what we see in simulations, and it kind of regarding angular momentum balance. It is a big question because what we see in simulations, we see also formation large scale flows, which evolve very slow in time, and fully answering your question, probably I have to run even longer. And problem is if some large-scale flows appear, it takes many dozens of hours to disappear and form kind of next large-scale flow. You see what I mean? So it means if I say do averaging, for instance, for 24 hours for very last period of time, and 24 hours for I don't know, say 50 hours apart. So it means the distribution will be different just because structure of large scale flows will be quite different, and make it. Yeah, I hope I answer on your question, but in terms of discuss on angular momentum balance, it's hard to say how long I really have to perform simulations to have enough statistics yeah, to answer your question. I don't know if Alan wants to comment this. I notice in chat, Alan.
Yeah, I mean, I could say a few words. There's with these sorts of simulations, we are talking about very short timescales that are covered by them, and anything that requires a study of a long-term balance would require a long simulation. We just they haven't been done. We haven't performed simulations for, say, months of solar time, at least not on this larger box. So yeah, we don't have an answer for you. We could investigate. It probably should investigate exactly what the dynamical balance is. It's an very interesting fundamental question. And if we perform that study, then we can either answer it quickly because we've already got enough data in the bank, or we'll have to run longer. That's the simulation question. It's open at this point. Yeah.
But you produce a shear in your layer, and you can go in and look at the velocities and calculate Reynolds stresses and so forth. I thought you already did that.
Well, yeah, I mean, they've been calculated, but the question is the statistically steady state we're in, I'll put steady in air quotes, really steady or not? In other words, if we might draw a conclusion about this number of hours, or 24-hour or so, that the plots were made from, but would that hold another 100 hours down the line, or another 1,000 hours? That's what it would have to be a tentative conclusion at this point. That's all I'm saying.
Okay, Sasha? Oh, sorry. Sasha's had his hand up for a bit.
Yeah, it's interesting that thermodynamic structure of this layer, because in sound speed inversions, which we have not discussed today, we can see also some very, very strong variations in sound speed inversions relative to solar model. And can we say that this leptocline is because of enhanced convection in the zone of hydrogen ionization zone? And mentioned that overshooting from this enhanced downdraft into the more stable layers beneath. It's not completely stable, but is it, so we see some splash in there?
Yes, I see some splashing, but it is, say, if I compare with my previous models of stars with shallow convection zone, you can see these splashes visually. But on the sun, because flows itself much weaker, you can see kind of like splashes in Reynolds stresses, or if you do kind of analysis, say, look RMS horizontal flows or something like this, so you really can see it. And also, what is interesting regarding transition between upper layers of convection zone, and if you go out below hydrogen ionization zone, we actually can see also changes in turbulent structure of convection. So it probably relates somehow, but yeah.
And there's a question from Nick in the chat. Does the model actually have helium ionization, or are you saying that the depth just coincidentally corresponds to that depth?
Yes, model itself have this layer, but I cannot answer on question if it is coincident. It just suddenly happened. Like I cannot answer on this because say I have to perform additional simulations and remove manually helium ionization zone or hydrogen ionization zone, right? So I cannot really answer on this question.
But your model includes ionization and latent heat from ionization and all this sort of stuff?
Yes.
Okay, cool. That's all I want to know. Thanks. Sorry, just going back, I was a little confused by your previous answers, though, when you're saying that you're not sure whether things are stationary, whether they're steady state or not. So, I mean, you're saying that the leptocline is a thing and it exists, and that's what you're explaining and stuff. But you're not convinced that the statistics are steady enough for Reynolds stresses for a near surface shear layer. I'm a bit confused about what is convincing and what is not in terms of statistically steady.
Okay, so what is convincing as we go closer to solar surface, it is more statistically steady state, right? It is first. Second is a reason why I'm not saying it is fully statistically steady state. It is very close to this, but it, as I mentioned, variations in relative angular momentum is less than 5%. So and how I cannot really say such variations relate because of turbulent dynamics or because it is not in fully steady state. I cannot answer this question, right? So it is a kind of big problem. And my personal concern about it, because we also have large scale flows, we actually say, if you have large scale flows with very low speed, you need to have long enough time averaging, right? And say when I did comparison for different periods of time, I see these general properties of leptocline are same, so it's not affected. But in terms of if we discuss about steady state conditions, my kind of personal concern as modeler, if you have large scale flows, you should have to do proper averaging. You need to simulate first statistically significant number of large scale flows, right? Say, for instance, I give simple example. Say, when we discuss about surface convection, we always discussing, say, if it is small box, we should have at least 5 granules to have more or less reasonable results. If it is 1 or 2 granule, nobody will trust you, right? And by analogy with large scale flows, I have maybe just a few such patterns. I see they appear and disappear. You see, but I cannot say I observe them like dozens of them, just because they evolve too slow. You see what I mean? So it, yeah.
Okay, thanks.
Well, thank you, Irina. We have arrived at the lunch hour, if you can arrive at a time. And we're a little bit behind in the schedule. And I know that what we had scheduled for 11 o'clock was going to be kicked off by, I believe, one of our European colleagues. Is that right, Anita? Are you in Europe?
Yes. Hi.
Yes.
That's
So,
true.
are you able to go in 1 hour and talk a little bit about early results
Yes,
from
yes.
FEE?
Yes,
Okay,
but
excellent.
it won't be very long. So yeah, sure.
Excellent. And then Kyle, are you okay being pushed back a bit?
Yeah, no problem.
Okay, awesome. Well, then we will reconvene at 1 o'clock Pacific time. And we'll lead off with a discussion of results from FEE. Thank you all.
Okay.